Hello, welcome everyone to our live stream about geometry in nature. Guess we should introduce ourselves. My name is David. I work at the Ontario Science Centre.
My name is Heidi, and I work at the Ontario Science Centre too. What a coincidence.
You might notice, though, that Heidi and I are not actually at the Ontario Science Centre right now. I am in my living room, but we are in the city of Toronto. And because we are in the city of Toronto, I think there's something important that we should recognize.
Yeah, we were not the first people here, and it's important to us to acknowledge that. So the Ontario Science Centre acknowledges that we are on the traditional territory of Anishinaabe nations, including the Mississaugas of the Credit and the Chippewas, as well as the Haudenosaunee Confederacy and the Wendat peoples. And it is now home to many diverse First Nations, Inuit, and Métis peoples. We are settlers on Turtle Island, and in the spirit of truth and reconciliation, we commit to respect, listen, learn, and support Indigenous peoples with whom we share this land and who have cared for this land since time immemorial. Thank you.
Thanks so much for that, Heidi. And I too am in the city of Toronto, like Heidi, but we're curious about where you are watching from. Are you from Toronto or are you watching from somewhere else? So feel free to share in the comments where you are joining from today. Now, I'll just bring up that slide I had before just to remind everybody about today's topic. So today's topic is called Geometry in Nature. And during our program today, a little bit later on, I will be asking you to maybe draw some shapes because geometry is, after all, the study of shapes. So if you have like a pencil or a pen, something to draw with, then we will be using that a little later on. So I just want to give you that warning so you have time to grab that if you want.
So David, I didn't take math or geometry in university, so I'm not that familiar with it. And so I'm kind of representing that kind of person in our audience. So I'm sure some of them are wondering, what is geometry exactly?
That is a great question, Heidi. I sort of hinted at it a bit before. Geometry is the study of shapes. It's like a type of math where we study shapes and volumes and areas, all sorts of things like that. So that's what geometry is, but why do we bother learning about it? What's it good for? That's our first question we want to ask you, the audience, is why is geometry important? Why do we even bother to study shapes? So the way you can answer is throw your answers into the comments wherever you're watching. And if you're watching together, like with your teacher or a parent, you could even tell them your answers. Or there's probably lots of adults watching as well. You know what to do. Let us know, why is geometry important? Why do we study it?
I know it is important. It's got uses. What might those uses be?
Let's wait a little bit, see if we start getting some answers in the chat, in the comments. But in the meantime, I think we should share some of the ideas that we came up with earlier when we were talking about it. So I'll just bring up this next picture. So here are some applications that we thought of. So geometry literally means earth measuring. And the first people to do geometry were probably farmers trying to figure out how much land they owned. So that's the bottom left corner there, is you can use geometry to measure a field. It looks like we have some answers coming in the chat. You see me looking off to the side, I'm just reading some of your comments. Looks like someone says to find harmony, help us understand the natural world.
Oh, and somebody said, do you need it for building?
Yeah, I think that's what a couple of these images show. Maybe you could talk about that, Heidi.
So absolutely right, you guys. As David mentioned, it's used sometimes for measuring out land and figuring out how to use it. But as you can see, so that's kind of one of the things that we're showing in the bottom left picture and on the slide. But as in the top left, there's a shape. David, what is that exactly?
It looks like some sort of triangle shape we've got going on there.
I think it's a wedge, and I bet you it's a wedge for making a sidewalk accessible.
In the top right, you can see somebody taking some measurements So geometry is all about measuring things. You know, when you're building things, you definitely need to measure. I know my father didn't necessarily follow that advice. He definitely didn't measure things before he cut them, but I think in general, it's good practice to measure before I cut. And Heidi, what's that delicious looking shape in the bottom right corner?
Quite possibly my favorite food, pizza. So yeah, geometry can also be used when we're cooking, especially for baking, because it's important to determine before you bake something the size and sometimes the shape, because that can affect how it's cooked and whether it's successful or not. So geometry is important in our kitchens too. We've got a couple of other answers here to determine space, aesthetics, perimeter area, architectural design, absolutely. Form of growth stages in plant life. Sometimes, yeah, there are different shapes that are involved in plant growth.
No, and even the cosmos, yeah, space itself is this super cool curved geometry. But we'll be talking about that more in a bit. All right. So we've introduced a little bit about what geometry is. So we can take down this picture now. We want to get a sense, though, of what you already know about geometry. So today in our program, we're going to be talking about 3 different types of geometry. And to get us thinking about the first type of geometry, we have this quiz for all of you. So let's bring up our picture and I will tell you how to do this quiz. So our quiz question for you, we want to test you. Can you name these shapes? So you can answer as fast as you can in the chat. Number 1, 2, 3, 4. What are each of these shapes? And Heidi and I will read out some of your answers.
It takes a moment for these answers to come in. So.
Yeah, and there also might be multiple correct answers for some of these. And if you don't know, that's completely okay too. You can say, oh, I don't recognize that one. Because not knowing things is actually a good thing because it means we have the opportunity to learn something new.
I recognize them. I'm wondering if our audience does.
All right, let's see. Somebody's saying number 3 looks like an oval. What do you think about that, Heidi?
Yeah, I would definitely say that qualifies.
Yeah, lots of people are saying number 1 is a hexagon, which, yeah, if you know that hex means 6, yeah, it's a 6-sided shape. That's a hexagon. Somebody is saying that number 2 is a rhombus.
I was going to say diamond.
It does look like a diamond. Yeah, a rhombus is a special type of shape called a parallelogram, but you're right. Number 2 is a special type of parallelogram called a rhombus. And what is anyone answering number 4, Heidi?
Yep. We have a couple of answers that there are people that think that number 4 is a trapezoid.
Oh,
Are they right?
Cool. A trapezoid. Yeah, it does look like a trapezoid. So either these are terms you've heard before or you're hearing them for the first time. But yeah, number 1, hexagon. Number 2, parallelogram or rhombus. Number 3, oval, or there's another name for it, ellipse, that I'm seeing some people say. And number 4, trapezoid. Great. So it seems like people already know a lot about this first type of geometry. So I'll take away that picture maybe now.
Now you said type of geometry. What do you
Exactly. So we're going to be talking about 3 different types of geometry today. And the first type is called this. It's called Euclidean geometry. It's named after this guy, Euclid, who was a mathematician who lived thousands of years ago. Some people even call him the father of geometry. But anytime you hear me say Euclidean geometry, what I really mean is flat geometry. That's like shapes that you can draw on a flat piece of paper. So for example, this heptagon I have here, a 7-sided shape, lies flat on my desk here. So that is an example of flat or Euclidean geometry. Now I have a heptagon here. I'm wondering, Heidi, and all of our viewers watching at home or at school, wherever you are today, what shapes do you see in your room around you?
Okay, I'll start. Oh man, I am seeing tons of rectangles. So there's the door and the lights, the switch plate for the light and the windows and my monitors and the shelves behind me and my phone. And okay, so let's start looking for some other circles. I've got a plate rail and there's some circles up there with the plates. And there's my clock, that's a circle, and it's trimmed with triangles. That's kind of fun. Sort of like I Spy. Oh, and there's a 7-pointed star shape in my window. What else? What other shapes are you guys finding at home?
For all I know, you could be making these up, Heidi. I can't actually see all of your room, but we're curious what you see in your room. What shapes do you see around you? So it could be ones that were made by people, or it could be natural shapes that you might have lying around too.
I'd turn my laptop around, but I think that might make people a little motion sick. Oh, I'm seeing a rectangle.
Right.
Oh, and we have a question about, I think it's referring to whether 2D is another way of saying Euclidean or flat. So 2-dimensional, is that correct?
Yeah, so something's Euclidean if it's flat, wherever you are, but you could also make a 3D shape where every single side is Euclidean. It's like a cube where it's flat on every side. It's a 3D shape, but all of the sides are flat. That's a great question.
And somebody's saying, is a chair a familiar shape? Yes, absolutely.
Yeah, and somebody's saying that they love the shape of your glasses. I assume that comment's for you, Heidi, because unfortunately I'm not wearing glasses. But if you want to compliment both of us, you know, I'd be happy to get some compliments too. I could use them, I'm sure. All right, I have another game for everybody watching at home or at school, wherever you're watching from. And I have a question for you too, Heidi. A little challenge. Sorry, I won't bring up that picture just yet. Just want to ask people to try this challenge. Because remember earlier I asked you to get something to draw with. So Heidi, do you have something to draw with?
Yes, I have a pen and a piece of scrap paper ready.
Okay, here we go. So here's what I want you to draw. We're going to try drawing a shape following these instructions.
Okay.
So I want you to draw a line straight down. Okay, now I want you to turn 90 degrees or a quarter turn. We call that a right angle, and draw a line straight to the right.
Okay. So it's looking like an L shape.
Okay, and then finally I want you to draw a line straight up.
Okay.
And I want you to tell me in the comments, what does your shape look like? And while you're answering what your shape looks like, maybe Heidi, you can show us your version.
Okay, this is what I drew.
What's it look like?
So it looks kind of like an open box or a glass.
Okay. What if I told you, Heidi, that you could follow my instructions exactly and yet draw a triangle instead of a box?
What?
Aha. Now there is a little bit of a trick to it, but I want to show you how to do just that. So I have here my marker, but instead of drawing on a piece of paper, I'm going to draw on something round, this orange. So I'll draw a line straight down, straight to the right, and then straight up. And I have, it's a little bit hard to see, the marker's not working so well in the orange. I have this beautiful triangle shape.
Oh my gosh. Okay, mind blown.
And that brings us to a second type of geometry called spherical geometry. It's a type of geometry that has to do with balls or spheres like this one. Now, Heidi, why do you think it's important for us to study spherical geometry?
Well, I mean, not everything is a shape that has flat sides. And honestly, like, we're on a sphere, right?
Yes, you nailed it. We are living on a sphere. So of course it's important for us to study the geometry of spheres, spherical geometry. We live on the Earth, which is an orange or sphere shape. Okay, so I'll bring up my next challenge for everyone now. It has to do with the idea of turning one type of geometry into another. So here we've taken a sphere, our Earth, and we've turned it into something flat, something Euclidean. My question for you is, which do you think is bigger, Greenland or Australia? So and Heidi, for our viewers watching at home, which one's which?
Just to be clear, Greenland is the top, the landmass that the arrow on the top is pointing to, and Australia is the landmass that the bottom arrow is pointing to.
That's our question. On this map, which is flat or Euclidean, which one is bigger, Greenland or Australia?
You can put, like, instead of typing the whole word, you could just type G or A.
I see lots of different answers coming in. I'm just reading some of your answers. Greenland times
like
10. 10 people are saying Greenland.
Super sure.
Australia is bigger. Greenland. Okay, I'm seeing lots of different answers coming in. Greenland. Okay. So
Okay,
here
most people
is
seem to be thinking Greenland.
another trick of geometry. So on this flat Euclidean map, it does look like Greenland is bigger. But in real life, in our spherical Earth, Australia is actually 3.5 times bigger than Greenland. It is way bigger.
Surprise!
Surprise. Okay, and the problem all has to do with this, which I'll just stop sharing that screen for a second. The problem is it's actually impossible to turn spherical geometry, so the geometry that takes place on something round like this, into flat or Euclidean geometry. To demonstrate that, I tried drawing different shapes on an orange. So I drew a rectangle, drew a circle, and I drew a triangle. And then I tried to take this orange peel and flatten it out. But watch what happened when I did that. I have a picture here that I'm going to show you to show how difficult that is. So Heidi, what do you think? So I've taken this orange peel and flattened it out. Do those shapes still look the same when I flatten them out?
No, they look, I would say distorted, which means misshapen, and also broken. I see you did it in 2 different ways, and both ways totally, they totally messed up the original shapes.
Yeah. It is impossible to take shapes from a sphere and turn them into this flat Euclidean geometry. So that's why I wanted to talk about this new type of geometry, which is called spherical geometry.
So the maps that we had in school I guess they did their best, but they couldn't actually do it like totally flat and make it actually totally realistic either.
Yeah, that's exactly right.
Okay, well, so we've talked about flat shapes, flat geometric shapes, and we talked about spherical geometric shapes, but there are other kinds of shapes out there that are neither, right?
Yeah, so like what do you have in mind?
Okay, well, there's things that you can even find them in your kitchen. So maybe we can show what I'm talking about, and in other places around us outside. So maybe we can see those examples. Okay, so what we're seeing here, the kitchen example I'm talking about is in the bottom right corner there, the lettuce and the kale. And these are shapes that they're not flat and they're not spherical. They are curvy, if you will. And then above the lettuce, we have a picture of coral and a sea turtle. And those also show curvy or ripply shapes, especially in the yellow coral on the left-hand side. And then the picture on the left of the screen is a picture of turkey tail fungus. So that's a kind of bracket fungus related to mushrooms, and it grows usually on tree trunks. And you can see there that is also sort of ripply and curved. So what kind of geometry are we talking about with those shapes?
That brings us to a third type of geometry. So I will show you. That is a great observation that you made there, Heidi. Okay, so I'll stop sharing my picture. I'll just bring myself up. So far we've talked about 2 types of geometry. We talked about flat or Euclidean geometry, which humans have actually known about for thousands of years. Talked about spherical or round geometry, which we learned about just a little bit after that. But it wasn't until fairly recently we learned about this third type of geometry called hyperbolic geometry, which is demonstrated by these potato chips. I'm going to show you. So Euclidean geometry is flat everywhere. Spherical geometry is curved everywhere, but it's always curved in the same direction. Hyperbolic geometry is actually curved in 2 different directions. So if you look here, it's curved this way. That's one curve, but it's also curved this way. And when something's curved in 2 different directions like that, we actually call it a saddle point, because it looks kind of like a saddle that you would like put on a horse. Here's my potato chip riding on my orange here. Aww. So this is that third type of geometry called hyperbolic. And the interesting thing about it, Heidi, which I know you were talking about earlier when we talked before this, is that hyperbolic geometry has existed in nature forever, but it was only very recently that humans figured out how to make it for ourselves. So maybe you could tell us more about that.
Yes, I may not have taken math and geometry in university, but I did study up for this presentation. So I found out that we've known about like Euclidean and spherical geometry for a very, very long time, like thousands of years in some cases. And geometers, the scientists who study and think about and try to explain geometry, they realized that there was another kind of geometry out there, but they didn't really, it took them a long time to figure out how to explain it. And that didn't happen until like the late 1800s, actually. And it didn't get really good until the middle of the 20th century, so in the 1900s. But that was explaining stuff that was already out there in nature, or that they had observed, like when they saw saddles on horses. But they didn't actually have a way to build those shapes themselves. We could build spheres and we could build flat shapes ourselves from scratch, but hyperbolic shapes, 3D versions, were really hard to figure out how to construct. And there was a geometer and mathematician in the 70s who created some with paper strips, but that was still using something flat that was originally flat to make something hyperbolic. It wasn't until the 1990s that this Latvian mathematician, her name is Dina Taimina, she actually realized that you could crochet hyperbolic shapes. So I don't know if everybody knows what crochet is, but it's that craft where you are looping yarn to create fabric. So she figured out that you could actually build a hyperbolic shape from scratch using crochet, which was kind of revolutionary.
Yeah, what does that look like? I see you have something in your hands there, Heidi.
Oh, yes, I do. My friend Christine dropped this off the other day. It's a hyperbolic crochet shape that she made with 2 different yarns. And as you can see, it's got that ripply shape that we saw in the pictures earlier. Now, one really interesting thing about hyperbolic shapes is that you can't actually flatten them out. So I'm going to just turn my camera. So no matter how hard I try, if I try to flatten out one part of the hyperbolic shape, it'll still come curling up in another part. Like that. See, it just, you can fold it so that you have a straight line. I'll just try to make that clear here.
Yeah, I can see that.
Yeah, but you cannot flatten it out to totally flat Euclidean shape. It just doesn't work.
Yeah.
Right. So what you're saying is that humans didn't really learn how to make hyperbolic geometry for ourselves until only like 20, 25 years ago. But nature has actually been making it for a long time, like all that lettuce and kale we saw.
Millions of years, hundreds of millions of years. Yeah.
Well,
in fact, the Science Center is going to be hosting a special exhibition about hyperbolic shapes in nature made with crochet, the crochet coral reef. And that's what Christine has been working on. So David, she also dropped one off for you, didn't she?
She did. And let's bring up our next picture to show everyone what that could look like. So I have a piece as well that Christine made. Thank you, Christine. So this is on the left is a coral reef, which exhibits this hyperbolic geometry that was made by crochet. And on the right is a real coral reef, and you can see the similarities. One made by nature, and nature's been doing it for millions of years. The other one made by humans, mostly women, and done very recently. So if you know how to crochet, there's all sorts of instructions you can look up online. You could try making something like this. But Heidi, what about for our friends who maybe don't know how to crochet? What could they do if they want to make hyperbolic geometries at their home?
Well, we do have 2 activities that we've posted on our OntarioScienceCentre.ca website. And one is using coffee filters, the basket kind of coffee filters that have that roughly kind of shape to them. You can thread them onto pipe cleaners in several layers and then shape them into something that looks a lot like coral. And there's also an activity called hyperbolic heptagons, sorry. And David showed you a heptagon or a seven-sided shape earlier. And interestingly enough, this is a way to make a hyperbolic 3D model, but using flat geometry. It's not like from scratch, but it is sort of basically you're recreating it. And so I've got my own version here. So I'll show that off. So I'll put I've got this all ready to tape up. So I'll tape it on here. You just have to sort of align the corners. And as you tape one shape to the next, you put them in the corner to corner and line up the sides, you will see that it actually starts to take on those hyperbolic directions, which I think is really cool.
All right, now I do want to save a bit of time for questions. So I have one more question for all of you, and then we will do our best to answer some of your questions. If you have questions, now's a good time to start putting them in the comments. I see a couple coming in. So the last question, we've talked about all these big fancy science and math words. So we just want to do a reminder. I'll bring up the last slide there. See if you can match these examples I have on the left with which type of geometry it is, because we talked about those 3 different types today. That top picture, that planet, would that be an example of Euclidean, spherical, or hyperbolic? So just match the letter with the number. You can put the answers in the comments and we'll read out some of your answers. All right, looks like we have some answers starting to come in now.
I'm sure most people have recognized that first shape or that first planet. Here we go.
Okay, let's see. Let's maybe bring up our answers. It looks like lots of people are answering. So what's that first one? A.
All right, so you've recognized that Jupiter there is the planet that we're talking about, and that is a sphere, so it's definitely number 2. Yep.
Okay, so maybe we can connect those.
Mm-hmm.
The next one, the paper airplane's kind of tricky.
Yeah,
the paper airplane is flat on all of its different sides, and it's made by folding up a piece of flat paper. So B actually goes with number 1. It's Euclidean geometry. And then finally, that bottom thing. What is that animal, Heidi?
Oh, that is a sea slug. They are amazing creatures, and they are naturally hyperbolic. So C is 3, and looks like most people were getting the answers absolutely correct. You guys are awesome.
Awesome. Well done, everyone. Okay. So we do want to answer some questions before we go. So let's take some questions from the audience. I see one here. It says, how were saddles made in the old days before discovering how to make hyperbolic structures? That is a great question. So a saddle point is something that's hyperbolic at just one single point, which means it's curved in 2 directions at this one point. If something is truly a hyperbolic shape, like our coral, it means that it's hyperbolic at every single point. So we knew how to make saddle points, but it wasn't until recently that we knew how to create something that is hyperbolic at every single point. That is a great question. Thank you so much for that. Let's see, what other questions do we have?
We have a question from Kai. Is it possible to take something flat and turn it into spherical geometry?
I might leave that question to the audience to test out for yourselves. See if you can take something flat, like a piece of paper, and turn it into a sphere. So if you have a piece of paper at home that you don't mind crumpling up, see if you can take your piece of paper and turn it into a sphere. That is a good challenge that I invite you to try. Okay, what other questions do we have?
Okay. Ooh, these are really good questions.
Yeah.
Are there any other types of geometry other than those 3?
Yeah, so usually
when we talk about geometry, we talk about Euclidean geometry, which is that flat geometry, and non-Euclidean geometry, which includes hyperbolic and spherical geometry. There's actually, you can do geometry in like higher dimensions than 3 dimensions. So yeah, there's lots of other different types of geometry. Technically, there's infinitely many types of geometry because you can have an infinite number of dimensions.
So
But
somebody has a question about fractal geometry and how it relates to hyperbolic, and so that's another example of another type of geometry that's a repeating type of geometry.
Yeah. You might have seen some
anything
really cool fractals before. You can definitely look them up. But yeah, I would say they're not really exactly the same, but they're definitely related. Okay,
Mhm.
let's see. What is a hyperbolic chamber? I don't know if I've actually heard of hyperbolic. Maybe hyperbaric chamber? Is that?
Yes, I have heard of
thinking?
hyperbaric. Baric refers to barometer or barometric pressure, and a hyperbaric chamber is a high pressure chamber. It's usually used for treating some diseases that have to do with lungs. So that's the difference. I don't think maybe there is a hyperbolic chamber out there that somebody's made, but I'm not sure.
I guess for like the fish that live inside those corals, technically the coral is a hyperbolic chamber for the fish.
Yeah, or the turtle shell that we saw earlier.
All right, let's see. I have time for maybe a couple more questions. Again, I apologize if we don't have time to get to all of your questions, but we will do our best in the coming week or so to answer as many of your questions as we can. Might be a written answer though. Let's see. Do you see another question here that we have time to answer now, Heidi?
Do cubes, pyramids, etc., fall into spherical category?
I would say that those, I guess it depends. So if you are like drawing things on like the edges of cubes, then you can get sort of weird geometries. Not really spherical, but non-Euclidean geometry. But if you're drawing something just on the flat surface of a cube or a pyramid, then that would just be Euclidean or this flat geometry. But yeah, you might get some weird things, sort of break some Euclidean rules if you try drawing shapes that go like over the edges of cubes and stuff like that. But I don't know if it would qualify as spherical or not. It's a really good question. I don't actually know the full answer to that.
What type of geometry is our kneecap? Ooh, that's a good one. I would say it's spherical in that it's sort of half of a sphere, a hemisphere. But I don't think that you could really say a kneecap is a hyperbolic.
Yeah, I don't think a kneecap would. But we do have something called saddle joints in our thumbs, for example. So our thumb has a joint where the bones kind of look like a saddle, like a potato chip. So we do have these saddle joints inside of our bodies.
That's a good point.
Not in the knee, as far as I know, though. I think it's in the thumb. Okay, maybe one last question, and then I'll give some homework for all of you watching at home to do.
Okay, you pick.
Okay. Let's see what's a nice one here. Can we crumple up the paper into a sphere? So that goes back to my other question of, can you turn a piece of paper into a sphere? I don't know. Will it turn out nice and smooth like an orange, or will it look all sort of wrinkled? I don't know. That's why I encourage you to try it yourself. See if you can make a nice round sphere out of a flat piece of paper.
That is a good challenge.
Okay. Now, I do want to encourage you to do what some of you are already thinking about, which is to try to look for some different types of geometry at home or at school, wherever you are, maybe outside. So look for things that are nice, have nice flat shapes, the ones that we usually learn about in school. Look for things that are nice round shapes, spherical. And maybe, Heidi, you could hold up yours again. Look for things that are all wrinkly, like this, that might be hyperbolic, things like lettuce. And if something's hyperbolic, remember, as Heidi showed you before, it can't be flattened out nice and flat. You can't iron it super well, I guess.
No, that would be frustrating. So if you do find some examples, we'd love it if you share them. We have social media accounts, like a lot of you are watching on Facebook already, and we've got our YouTube channel as well and Twitter. So share some photos if you want of things you're finding out there that are examples of geometry in nature. We will be posting this presentation on those sites. And if you have any other questions that we didn't get to, you can send them to scienceathome@ontariosciencecentre.ca. So easily remembered. And the PDFs are available if you click on the Science at Home page on our website. So thank you so much for coming out, for clicking on this today. We're super excited to present this to you guys.
All right, I had a lot of fun. I hope that you did too, Heidi, and that all of our viewers did. I have so many oranges and potato chips that I have to eat now. I hope you have a great day, everyone.
I'm craving potato chips now too, yes. Thanks, everybody. Have a great day.
Bye.
Remember,